Good day everyone, I'm Junji Politud from Best Ed 1A, and as of today, we will be discussing about chi-square test. So, what is chi-square test? A chi-square test is basically a data analysis on the basis of observations of a random set of variables. Usually, it is a comparison of two statistical data sets. This test was introduced by Carl Person in the 1990 for categorical data analysis and distribution. So, hence the name Pearson's chi-square test. This test is used to estimate how likely the observations that are made would be by considering the assumptions of the null hypothesis as true. So if you want to test a hypothesis about distribution of a categorical data variable, you need to use a chi-square test or another non-parametric test. The categorical variables can be nominal or ordinal. It can represent groupings such as species or nationalities because they can only have a few specific value and they can't have a normal distribution. The chi-square test distribution was used to test the relationship between two categorical variables. So there's actually three kinds of tests that is included or hedged in the chi-square test. Those are the tests for goodness of fit, which are the data that are in frequency distribution, and the test for independence that uses the contingency table. And the last is the test for homogeneity, the test for proportions. So let's go to the first test that is part of the chi-square, the test for goodness of fit. So what is the chi-square goodness of fit test? It is a test that is a statistical hypothesis that's used to determine neither a variable is likely to come from a specified distribution or not. It is often used to evaluate whether the sample data are representative of the full population. The goodness of fit tells you that if your sample data represents the data you would expect to find the actual population. More specifically, it is used to test if sample data fits a distribution from a certain population. You are testing to see whether a frequency distribution fits a specific pattern. You can use the chi-square goodness of fit test. So here's the formula for the chi-square goodness of fit test. This formula is also used in the other test which had been said in a few moments ago. As with the degrees of freedom equal to the number of categories minus 1, and where 0 or O is the observation frequency and the E as the expected frequency. The formula being x squared or chi-squared equals the summarization of the observation minus the expected value squared over the expected value. So in order for us to understand how the goodness of fit test formula is used or applied, we will answer a sample problem that includes the solution and the steps on how to solve using the Pearson's formula. So here's the sample problem, and it's about the homeschooled students' activities. So homeschooled students often attend to their local school to participate in various types of activities such as sports or musical ensembles. According to the government, 82% of the homeschoolers receive their education entirely at home, while 12% attend school up to 9 hours per week and 6% spend up to 9 to 25 hours per week at school. A survey of 85 students who are homeschooled revealed the following information about where they receive their education. The alpha being 0.05, but supposedly there would be a small letter A before the equal sign, but due to the problems with the presentation, it didn't appear. It was supposed to be shown since the alpha or the 0.05 is supposed to be used in finding the critical value, which will be discussed later on. The value 0.05 is there as a sufficient evidence to conclude that the proportions differ from those stated by the government. And the table below shows the categories or the distributions of the survey made by the 85 students. So let's go to the solution and the steps of our sample problem and how the formula is used. So the first step is to state the hypothesis and identify the claim. So there are two kinds of a hypothesis, the null and the alternative hypothesis. But first, let's briefly discuss these hypotheses. The null hypothesis is a test that always predicts no effect or no relationship between variables, while the alternative hypothesis states your research prediction of an effect or relationship. So let's get back to the problem. The null hypothesis is where the statement of the government is accurate as it has been, having 82% homeschoolers receive their education entirely at home, while 12% attend school up to 9 hours per week at school, which is the claim, while the alternative hypothesis is where statement of the government doesn't have an accurate distribution. So let's head to the step 2. The step 2 is finding the critical value. So in order to find the critical value, first we need to minus the number of categories to 1 or n minus 1. Therefore, 3 minus 1 equals 2, with the alpha being 0.05, thus having a critical value of 5.991. You can see in the illustration where the 2, which is aligned to the number of 591, which is under the 0.05. The illustration below is called the chi-square test table, which is used to determine the critical value of a test or a hypothesis. So let's go to another step, which is to compute the test value. So to compute by subtracting the expected value from the corresponding observed value, squaring the result and dividing by the expected value and find the sum. But before we compute the value, first we need to find the expected value of each of the categories. On the category on entirely at home, you need to multiply the preferential value, which is 82%, by the total number of students that had been surveyed. It goes the same for the other categories. So 82% will be converted to 0.82 and will be multiplied by 85, which equals to 69.7. The category up to 9 hours is 12%, multiplied by 85 equals to the expected value of 10.2. And the last category is the 9 to 25 hours, which is 6%, multiplied by 85 equals to the expected value of 5.1. Therefore, the answers filled the blanks at the expected values and it completed the table. So here's the computation on how to get the test value. With the use of Pearson's formula, the chi-squared equals to the summarization of observation frequency or observation values minus the frequency squared over expected frequency. So now we substitute and it would end up as x squared equals to 50 minus 69.7 squared over 69 plus 7 plus 25 minus 10.2 squared over 10.2 plus 10 minus 5.1 squared over 5.1. If solved, it would equal to 5.56 plus 21.4 plus 4.7, which is equals to 31.66. The 31.66 will be the test value, which will be put into decision whether if it would be rejected or not. So here's the step 4, which is the decision rule, where you make a decision on whether you reject the claim or the null hypothesis. Depending whether your test score is lower than the critical value. So let's look into this diagram or graph of a wave which shows the decision you are going to make. It is laid there, a wave, and it can be seen that there's a yellow shaded part, and the yellow shaded part refers to the part that rejects the hypothesis if the test value is greater from the critical value, which borders the rejection and not the rejection area. The not rejection area is the area that hasn't been shaded, which means that if your test value is lesser than the critical value, then it would be placed at the not rejection area, thus not reject the null hypothesis. But for the sample problem, the test value is much greater than the critical value, placing it in the shaded area, which it will be rejected, thus rejecting the null hypothesis. The last step is the conclusion or the summarization of results. It stated that there is enough evidence to conclude the rejection of the null hypothesis regarding the statement about the distribution of the homeschoolers. And that solves our sample problem. So in this another slide, I'll show you the full steps of the chi-square goodness of fit test. This is the simpler and the overview of the steps. But before we continue to the next reporter, let's first discuss the test that uses contingency tables. A contingency table is designed as an R times X or rows by columns table. In this case, R equals 12 and column is equals to 3. Hence, this table is 2 by 3 contingency table. Each block in the table is called a cell and is designated by its row and column position. For example, the cell with a frequency of 80 is designed as a C1, 2, or a row 1 and column 2. The cells are shown below. The degrees of freedom for any contingency table are rows minus 1 times columns minus 1. And that is the degrees of freedom, which is equals to R minus 1 times column minus 1. In this case, 2 minus 1 times 3 minus 1 equals 1 times 2, which equals to 2. The reason for this formula for the degrees of freedom is that all the expected values except 1 are free to vary in each row and in each column.
Hi everyone, I am Mark Steven Tandoy and I'll be continuing the topic by discussing the one of the tests that is part of the test of chi-square tests, the chi-square test for independence. So what is chi-square test for independence? The chi-square test of independence is a statistical hypothesis test used to determine whether two categorical or nominal variables are likely to be related or not. Like all hypothesis tests, the chi-square test of independence evaluates a null and alternative hypothesis. The hypotheses are two competing answers to the question, are variable 1 and variable 2 related? So, when and why is the chi-square test for independence used? The chi-square test of independence is used to determine if there is a significant relationship between two nominal or categorical variables. The frequency of each category for one nominal variable is compared across the categories of the second nominal variable. The data can be displayed in a contingency table where each row represents a category for one variable and each column represents a category for the other variable. For example, say a researcher wants to examine the relationship between gender, male versus female, and empathy, high versus low. The chi-square test of independence can be used to examine this relationship. The null hypothesis for this test is that there is no relationship between gender and empathy. The alternative hypothesis is that there is a relationship between gender and empathy. Example, there are more high empathy females than high empathy males. So in order to know whether these two have any significant relationship, we need to use the process of the chi-square test independence. So in order for us to further understand the process on how to solve or on how to apply the chi-square test for independence, I will give you two categorical variables which we will be comparing or to determine if whether these two have a significant relationship. This sample will help you understand the problem and its steps and processes on how it will be solved. The two categorical variables are the alcohol and gender. A researcher wishes to determine whether there is a relationship between the gender of an individual and the amount of alcohol consumed. A sample of 68 people is selected, and a date or information is being laid in a contingency table in the picture below to be used as referential digits that will be used to solve and examine if the two have a relationship. So here's the table where the gathered information lies, which we will be using in order to solve the test. The total sum of each of the columns are already added because the sums and the given numbers we will be using to solve for the expected value. So here's the solution for the sample problem including steps. which will guide you to solve for the independence of each of the categorical variables. The step 1 is the stating of the hypothesis and finding the claim. So, the null hypothesis of the sample problem is the amount of alcohol that a person consumes is independent of the individual's gender, or is independent of the individual's gender. While the alternative hypothesis is the amount of alcohol that a person consumes is dependent on the individual's gender. Which is the claim? So, with that, we need to formulate the problem to determine if the null hypothesis is to be accepted or not, and same goes for the alternative hypothesis. So let's continue to the step 2, the finding of the critical value. Since the alpha is already given as the 0.1, all we need to solve for the degrees of freedom, which is solved in a different way compared to the first, the goodness of fit test. So in order to solve for the degree of freedom, we need to subtract the number of rows by 1, and same goes for the columns that will be subtracted by 1, and the difference of the two will be multiplied. Thus, the product became the critical value. So in this problem, we will be subtracting the number of rows, or 2, by 1, which equals to 1, and the number of columns, or 3, will be subtracted by 1, equals to 2. Then 1 and 2 will be multiplied, who are the products. 2 being the degree of freedom and 0.1 as the alpha, it would give us 4.605 as the critical value. As you can see, where the DF, or degrees of freedom, is aligned to 4.605, which is below the alpha. With our critical value being done, we can now solve for the test value. But before we solve for the test value, first, we need to solve for the expected value. The expected value's formula is expected value is equals to the row sum times the column sum over the grand total. So the computation is already laid out. E1, 1 meaning expected value equals to the total of row 1 over the grand total. Continue and compute for every sum of rows with the every sum of the columns until all the expected values have been solved. Here's the complete table where the expected values has already been put beside the observation value. So now, let's compute and find the chi-square test value using the formula chi-square equal to the summarization of observed value minus the expected value square over the expected value. So we need to solve each value that has already been computed and add up every sum of the computed values. So with the result, we can now decide whether we reject the claim or to accept it. So, the illustration shows that the result was laid in the non-shaded part, so that means the decision is to not reject the null hypothesis since 0.283 is lower than 4.605. So let's go to the summarization of the results, which states that there is not enough evidence to support the claim that the amount of alcohol a person consumes is dependent on the individual's gender.
Alright, so I'm John C. Peralta from BizEd English 1A, and today I'll be discussing to you the second chi-square test, which uses a contingency table and called the homogeneity of proportion test. A test of homogeneity compares the proportions of responses from two or more populations with regards to a dichotomous variable, or variable with more than two outcome categories. In this situation, samples are selected from several different populations, and the researcher is interested in determining whether the proportions of elements that have a common characteristics are the same for each population. The sample sizes are specified in advance, making either the row totals or column totals in the contingency table known before the samples are selected. Alright, let's have an example. So let's say, according to the American Automobile Association, 31 million Americans travel over the Thanksgiving holiday. To determine whether to stay open or not, a national restaurant chain surveyed 125 customers at each of 4 locations to see if they would be traveling over the holiday. So in order to test the claim whether if the proportions of Americans who will travel over the Thanksgiving holiday are equal, we need to use the chi-square test for homogeneity of proportions. To determine whether the proportions of elements that have a common characteristics are the same for each population. The sample sizes are specified in advance, making either the row totals or column totals in the contingency table known before the samples are selected. So in order for us to truly apprehend and to further understand how is the test of homogeneity of proportions is used, such like the other two tests that has already been discussed, we made a sample problem where we can learn the process on how to test the hypotheses of the said proportions and how it is used. So let's have a sample problem regarding a grocery list. The vice president of a large supermarket chain wished to determine if her customers made a list before going grocery shopping. She surveyed 288 customers in 3 separate stores. The results are shown here. At alpha equals to 0.10, test the claim that the proportions of the customers in the 3 stores who made the list before going to shopping are equal. So here's the table where the data has been laid out, having 3 columns consisting of the stores that has the same proportions of 96, and row 1 with 219 and row 2 having 69. Let's start with the step 1, the hypothesis and finding the claim. The null hypothesis claiming that proportion 1 is equal to proportion 2 equals to proportion 3 equals to proportion 4 and so on and so forth. For short, all the proportions are claimed to be distributed equally, while the alternative hypothesis states that at least one proportion is incorrect or is different from the others. The step 2 is to find the critical value with the same process test of independence by subtracting the number of rows by 1 and multiplying it by the difference of the number of columns by 1. Therefore, the degrees of freedom is 2 with alpha as 0.05. So with the use of chi-squared table, we can find that the critical value is 5.991. To compute the test value, first compute the expected value, with the formula expected value equals to the row sum multiplied by the column sum over the grand total. With that formula, you can now solve for the expected value, with row 1 and column 1, along with the columns 2 and 3, is equals to 219 times 96 over 288 would equal to 73. Meanwhile, all the expected value in the row 2 have the same results like all the results on row 1. The expected value is 23, with all the values in the table solved. And when all the expected value is already been solved, you can put it beside the observed values. With that, we can now solve for the test value. We can use Pearson's formula where you can solve for the test value by subtracting the observed value with the expected value squared over the expected value. If we compute every observed value and expected value in each cell of the table like what's in the presentation, we can solve for the test value, which overall summed 2.37. Next is step 4, or the discussion rule, where we decide whether to reject the null hypothesis or not. But for the sample problem, the decision is to not reject the null hypothesis, since 5.991 is greater than the test value, which is 2.37. After we decide, we could summarize the result, which states that there is not enough evidence to reject the claim that the proportions are equal. Hence, it seems that there is no difference in the proportions of the customers who made a list before going shopping to the 3 stores. Here's the overview illustration of the steps in the chi-square test of independence and the test for homogeneity of proportions.